So let's talk about the Crenarchaea. These organisms were originally just a handful of things, but a lot of effort has been put into finding new ones. I mentioned earlier that there was a German effort to isolate as many different kinds of archaea as possible. And this is where these sequences come from, and where these organisms come from. The reason for this is because there was a lot of interest, and there still is, in organisms kind of at the limits of life. Organisms that live at really high temperatures, or really acidic conditions, this sort of thing. Because that has a lot to tell you about how life works and where it could be. And so NASA, for example, put a bunch of money into life at high temperatures. They're now putting a bunch of money into life at low temperatures because of their searches for evidence of life outside of planet Earth. So there are basically 4 kinds of Crenarchaeas. There are Thermoproteus, Caldospheras, which are unusual, Desulphirococcus, and Sulfolobus. Essentially, all of the cultivated organisms in this group are sulfur-metabolizing thermophiles. I'll talk about that sulfur metabolism in a minute. Interestingly, though, if you look in natural environments, you see Crenarchaeal sequences all over the place. And there are cases of Crenarchaeas, lots of them, in cold environments. The sea is full of them. If you go below the surface, the top couple of hundred feet of the ocean, and sample from the bulk non-lighted water of the ocean, typically something around 30% of the organisms you find are Crenarchaea. This one, Crenarchaeum symbiosum, is the best studied of these things. This is a symbiont of a cold water sponge. It lives in the cilia of these sponges. You can't grow it. It can only grow in contact with this sponge. What it's doing there, nobody knows. So there's this dark matter of Crenarchaea that we know are really common in the environment, but we don't really know anything about them. And so when people say that archaea are extremophiles, that's really only true of the cultivated species. It probably is not a general property of the group as a whole. The cultivated species predominantly carry out one of 3 or more than one of 3 kinds of sulfur metabolism. Some of them carry out sulfur reduction, where you take hydrogen and sulfur and make hydrogen sulfide. And you use this to generate a proton gradient. These things are anaerobes, as you might imagine, and are autotrophic. Hydrogen's the electron donor, and so you generate those protons, and that's where you get a proton gradient. So this is kind of a sulfur respiration of sorts. It's just that you have the hydrogen half reaction coating electrons and the sulfur to hydrogen sulfide is the reduction part of the half reaction. There is sulfur respiration. We've talked about this already. This is standard issue respiration, only instead of oxygen, you're using sulfur. And that means you're heterotrophic, you're using carbon, fixed carbon, acetate, and all that kind of stuff. Goes into central metabolism. You make FAD or NADPH, and that feeds into electron transport. It's just that you're using sulfur instead of oxygen at the end. And so the organics end up as CO2, and the sulfur ends up as hydrogen sulfide. Many of these organisms can also grow by aerobic respiration. They usually grow better by sulfur respiration, but you can also grow them aerobically. Or they can grow by sulfur oxidation. This is a heterotrophy. So they're using organics from the media for carbon, but they're getting energy from just the straight oxidation of sulfur to hydrogen sulfide. Obviously, if you're using oxygen to get energy, you're an aerobe of some kind, or at least a microaerophile. So thinking particularly about the top 2, These things are anaerobes. This is common in this group of organisms, probably at least in part because oxygen is not generally available to them. Most of these organisms are thermophiles, and I think I've mentioned already that the solubility of oxygen in water is profoundly sensitive to temperature. And once you get up to the kind of temperatures that these organisms, most of them grow at, there really isn't very much oxygen in water anyway, unless you pressurize it or do something to drive the oxygen into solution. Most of these organisms, in addition to using sulfur, can use other kinds of sulfur compounds, things like thiosulfate. This is important because the melting point of sulfur in water is actually pretty low. And some of these organisms grow at temperatures that are above the melting point of solid sulfur. And so obviously if you've got this fine powder, that's a great thing to try to grow on. But if that melts into a spherical globule of molten sulfur, that's really not available to the organisms that access. And so having things like thiosulfate or dithionite are better substrates for the growth of these creatures. Also, it's a lot easier on your cultures, right? Having a swirling a flask that's got this yellow powdery stuff in it is a nightmare. Again, most of them are thermophilic, and many of them are extremely thermophilic. Organisms that grow above the temperature of 80, and some of them grow much higher even than that. There's another group, so I mentioned the sponge symbionts. There's another group that carry out this amazing process called anaerobic ammonia oxidation. We talked about that when we talked about the planktomyces, in which the anaerobic oxidation of ammonia, one of the intermediates is hydrogen. And how these organisms deal with that is entirely unknown. So what kind of environments do these live in? I've shown you some pictures of this already. So here's the pit in Yellowstone, like Moose Pool and those kind of environments. These are moderately low pH, at least by archaeal standards, 2 to 3, maybe 3.5. 80, 85 degrees. These are the perfect environments for these kind of organisms. Now, one group of these creatures, the Thermoproteus and relatives, are generally rod-shaped or filamentous. And so here's Thermoproteus tenax. You can see, if you look carefully, that this organism has an S layer, so it's got a semi-crystalline protein envelope, a cell wall. Notice the way it's dividing. That looks pretty weird, doesn't it? What's happened is, this is the mother cell, and it starts off here with a bud. This is the growth plate, right? As a rod-shaped organism, you've got hemispherical caps, a cylindrical body, and then cell wall and cell membrane is added in these circles where all the elongation of the cell takes place, the growth plate. And the bud forms there, and then grows out into a full-size organism. And that's typical of these creatures. It's either growing either by elongation to filaments or through budding. These things are strict anaerobes. They grow by sulfur respiration. Some of them can grow heterotrophically, but not always. This thing grows at 85 degrees. It is motile. There are flagella on this. Here's one. But again, I've mentioned this before. If you look in the literature, it will tell you it's non-motile. You can't have flagella and be non-motile, right? And this is because they look at them under a microscope slide at temperature. This thing likes to grow at 85 degrees. It isn't motile at that temperature. There's another, the Pyridictium and relatives. This is Pyridictium occultum. Typically have the morphology, essentially a flattened disc that they're connected together. Think of it the kind of stereotypical Western cactus. I can't remember the name of the ones you see in gardens and stuff, but they're kind of irregular, flattened things connected together. prickly pear cactus. Most of the organisms in this group had these tubules that connect them together. These are cell envelopes, so their cytoplasm is actually connected together. You can't see this under a light microscope, of course. What they're doing there is not known. Pyrodictyum occultum is one of the most primitive organisms known, and it is also one of the most thermophilic. It grows, I say 115 here. There's some isolates that grow pretty well at 118 or 119 degrees. That's spectacular. This thing could grow either by sulfur respiration or by sulfur reduction. And they're obviously isolated in environments like deep sea hydrothermal vents. To grow at these kind of temperatures, you have to have pressure to keep the water in solution. Turns out you don't need that much, by the way. So how deep in the water do you think you would have to go to raise the temperature to 150 degrees centigrade at sea level? That's pretty close. 45 meters. And that's above the growth temperature of any cultivated organism right there. But these things are from hydrothermal vents, also from vents near Iceland and places like that. Yeah?
What is the aspect?
One time. Yeah, so there's good evidence for growth up to 145, I think it is. These are from in situ growth lines. So if you take a thing and put it on top of a hydrothermal vent with growth surfaces, you can monitor the temperature, and in call them vent caps. In these vent caps, there's good evidence that where water flow through the system was 145 degrees at colonization of these surfaces. So those organisms grew and colonized the inside of the machine at 145 degrees. None of them are cultivated. So don't worry about that. This is Sulfolobus. This is a fun organism. It's more or less spherical. It's kind of rough, irregular spheres. The reason that they're not nice, smooth spheres is because, just like yeast, every time this thing divides, it divides by budding. Every time it divides, it leaves behind a scar. And so you get this kind of lumpy, lobe-looking organism after it goes through a bunch of divisions. Probably, like yeast, this means that once the entire surface of the cell is covered in budding scars, it can no longer divide. Of course, its offspring can, because they're free of budding scars. These things are really common in solfataras and mud pots. This thing is an obligate microaerophile. It does sulfur oxidation or respiration. It grows at pH 4.5. That's not actually so acidic. Some of its relatives, one of its relatives is Metallosphaera sedula. Really, really cool organism. Grows at 85 degrees, pH 0. That's 1/2 molar sulfuric acid. Sulfolobus has been used to study a really interesting process called fatty acid toxicity. So, let's say you're an organism. Well, one that looks like this and not one that looks like that. The pH inside is going to be about neutral, right? Let's say the pH out here is not neutral. If you're a heterotroph, you're probably going to run into compounds that look like this, right? Fatty acids, acetate, propionate, all that kind of stuff. I drew this with an H on it, didn't I? Why did I do that? It's acid, right? It's an acid environment. It's going to be protonated. It's pH 2, the pK of acetate is about 3.5. So at pH 2, almost all of it's going to be protonated, or any particular molecule is going to be protonated the vast majority of the time. when this thing goes wandering through the liquid environment, what's it gonna do when it hits that envelope? Yeah, it's gonna go through, right? The membrane isn't gonna be any particular barrier to this, and so it's gonna go in. What's gonna happen then? The proton's gonna fall off. Now what's gonna happen when this thing bumps into the membrane? Nothing. It's not going to go through. It's charged. It can't go through the envelope. The result is that if you put acetate in a culture of sulfolobus, the cells die like that. This is an uncoupler. It immediately decomposes the proton gradient. The acetate flows into the cell, dumping protons in and acidifying the cytoplasm and killing the cells. That's pretty tough for an organism that's a heterotroph, isn't it? You've got to be very careful. You've got to feed them the right kind of stuff. You've got to feed them things like amino acids in low concentrations. You have to be very careful with the cultivation conditions because although they require organics and they require low pH, they require them in just exactly the right form. And that probably is this kind of reason why a lot of these organisms are so hard to